Okay, so now let's start our evolution of the universe. We are going to begin with time t equals 10 to the negative 43rd seconds. So prior to this point in time, we don't know what the universe was like because the laws of physics did not operate the way that they do today. So we think that the force that would have controlled the universe prior to this point in history would have been tau. But we don't know what the temperature of the universe was. We don't know what the size of the universe was. And we also don't know anything about the time prior to this time in history. So we're going to begin with this point in time, 10 to the negative 43rd. So tau breaks apart into gut and gravity. So we're calling this part 1. The forces are beginning to decouple. They're coming apart. And then what was the temperature of the universe? 10 to the 32 Kelvin. And then the size is 10 to the negative 35th. So notice this is Planck time, Planck temperature, and then Planck length. Okay, so what was the universe composed of during this time period? So it would have been composed of Qs, so that's going to be quarks, and then a Q that has a bar over the top of it means an anti-quark, antimatter. A Q that has a tilde over the top of it means it was a supersymmetric quark called a squark. So when we in our previous lesson we talked about supersymmetry and superpartners. So the superpartners to the quarks were the squarks, and their job was to be able to communicate with the carriers of the various kinds of forces. Don't worry about it. All right, then you've got L for leptons, so electrons and neutrinos. And then you also have an L that has a bar over the top, so that would be a anti-lepton. And then you also have leptons that have a tilde over the top of them. And so those would be sleptons, so the supersymmetric partner to the lepton. And then you got light, so different kinds of electromagnetic radiation. And then you've got dark energy. So all of these things existed right after the Big Bang occurred. Now, what were these particles doing? Okay, they had so much energy that they could spontaneously form and then be destroyed. So what do I mean by that? Okay, according to Einstein, E equals mc squared. So that if you've got enough energy, you can create matter and antimatter. Matter and antimatter, when it goes back together again, makes energy. So what's happening is that these quarks and antiquarks are being formed out of the heat of the Big Bang, but then they're going back together again and turning back into energy. So energy and matter are in equilibrium at this point in history. All right, another thing I want you to notice is that dark energy was weaker than gravity because dark energy depends on distance. So this gets back to the previous lesson when we said that the force of gravity may have two parts to it. So the first part is our traditional force of gravity, which is minus big G m1 m2 divided by r squared. So that's how we normally think of gravity, and it's always attractive. But then in order to account for dark energy, maybe the force of gravity has another part to it that depends on distance. And so this is positive as opposed to negative. So this term of gravity would be expansive, and it would cause the universe to expand. Okay, but this term is going to be stronger initially because the distance is so small. So this term only starts to become dominant when you get out to the size of galaxy clusters. Okay? So now, at this point in history, gravity is stronger and it's the dominant force in this. So dark energy is not very strong at this point in history. Also notice that the Higgs field has formed. So what did the Higgs boson do? The Higgs boson was what caused mass, particles to have mass. So and mass causes gravity. So if you're going to have gravity, you got to have the Higgs field as well. Okay, let's go on here. So now we're going to go to 10 to the negative 35th seconds after the Big Bang. The temperature has cooled down to 10 to the 28th Kelvin, and the size of the universe has gotten larger. Okay, now keep that in mind. That would be something that you would be needing to tell me on the exam, that the temperature is getting cooler and the size of the universe is getting larger. So what about the forces? So what has happened to them? So notice now that gut has broken apart into the strong nuclear and the electro-weak forces, and you still have gravity. So now there are three fundamental forces that control the universe. So the forces are continuing to decouple. Now notice the composition of the universe is exactly the same as it was before. So don't worry about this part. So there are still fundamental particles. They're changing into energy. Energy is changing back into those fundamental particles. But at this point, we don't need to know what's really going on. So let's concentrate on what these forces are doing. Now, when gut changed into the strong nuclear and the electro-weak, that caused a thing called inflation. So that the universe greatly expanded. So space and time expanded as a result of inflation. How much? The size of the universe is going to go from 10 to the negative 24th meters to 10 to the negative 2 meters, which is about the size of a grapefruit. Now you might say, well, a grapefruit's not that big. Well, when you're starting off 1,000,000 times smaller than a quark, and then within this time period, you're going to the size of a grapefruit, well, now all of a sudden, that's pretty impressive that happens. So this is the beginning of inflation, and then this is the end of inflation. So at the end of inflation, you still have these same forces that you did before. It's just that the universe has gotten larger. Now, what exactly is inflation? So here's a way of thinking about it. Think about what dry ice is. Dry ice is a solid. But if you put it on the table, it starts to smoke because it's changing from solid dry ice to gaseous carbon dioxide. So when it is a solid, it's very ordered. The molecules of carbon dioxide are lined up side by side and locked into position. But when it turns into a gas, that carbon dioxide's anywhere, it can go anywhere that it wants in the room. It's disorganized and it takes up more space. So similarly, when you had gut, things were organized. And then when it turned into these two forces, it became disorganized and took up more space. So that's one way of thinking about what inflation was. Okay, so now we are at the end of inflation. Notice that the particles are still the same. So we're concentrating on what's happening to the forces. Okay, now we'll go forwards, and now it is 10 to the negative 10th seconds after the Big Bang. The temperature of the universe is now up to 10 to the 15th Kelvin, And the size of the universe is now up to 10 to the 39th meters. Okay, so this is 1/trillionth of the current size of the universe. So it's still pretty small. The constituents of the universe, it's still the same. So nothing has happened here. But notice what has happened. So at this point, now you've got the strong nuclear, and then the electromagnetic, and then the weak nuclear, and then gravity. So now you've got 4 fundamental forces that are controlling the universe. So what have we said happens in part 1 is the forces are decoupling. Okay, so now we're ready to go on and talk about what's going to happen to the particles. And that's going to be part 2. So I'll see you in just a moment.